Hello everyone, welcome to our course Lateral Torsional Buckling of Beams and Girders, Basic Principles of Steel Structure. Now, here is the content of this chapter 3.2.1, Review of Conventional Beam Theory, 3.2.2, Flexural Design for Lateral Torsional Buckling. Now first, elastic beam theory. Steel structural beams are typically designed based on simple beam theory. The fundamental assumptions of simple beam theory include small deformation. Plane remains plane, i.e., linear distribution for strain in cross-section. A stress-strain relationship is given as F equals F epsilon, and within the range of the yield strain, F equals to E epsilon, where E is a modulus of elasticity. A plane section can have two principal axes based on the direction of the applied moment vector. A beam can be bent about its strong axis or weak axis and can be bent in a biaxial bending condition, as shown in Figure 3.4. A plastic moment. The above theory only works for the case where the whole section remains elastic. If the elastic limit exceeded, in order to examine the post-yielding performance of a bending, remember, the assumptions must be reconsidered. Experimental evidence indicates that the second assumption can still be applicable for post-yielding behavior. The third one must be modified, i.e., the Hooke's law must be abandoned. Now let's look at elastic lateral torsional buckling. If the compression flange is not fully braced or supported along the length of a beam member, flexural lateral torsional referred as FLT or LTB buckling may govern the behavior of the beam. As shown in Figure 3.5, this failure mode is a combination of a lateral buckling mode and a torsional buckling mode. The general theory of elasticity on lateral torsional buckling of beams is introduced in this section. Let's consider an I-beam subjected to a constant moment applied in the plane of web, as shown in Figure 3.6. Now, you can see Figure 3.5 shows the developing process of lateral torsional buckling of beam. Now, let's look at the end condition. Rotations about X and Y are free, therefore warping is free also. Torsion about Z is restricted. Such conditions can be achieved by providing transverse stiffness at end supports. The critical buckling moment for simply supported beam with a moment distributed constantly, which is expressed as the formula 3.13. The inelastic LTB due to residual stress. The elastic LTB critical moment has an upper limit MR, which is yield capacity considering residual stress, FR, which is expressed as a formula 3.14. From formula 3.13 and 3.14, solve for the lengths LR corresponding to MR. We have the following expressions of 3.15 to 3.16, where the parameter x1 and x2 are expressed as the formula 3.17 to 3.18. Now, here is the plastic design limit. For compact section beams, the moment capacity is dependent on buckling or embraced length LB. When LB is sufficient short, LTB can be avoided and the beam can develop the full plastic strength. This limit length of LB is expressed as LP. Theoretically, such equation for LP is corresponding to H or I-shaped section. However, considering imperfect supports and residual stress, AISCS sets, LP can be expressed as a formula 319, where Ry is radius of gyration about y-axis. To assure a greater deformability to allow plastic design, a lower limit should be established. AISCS specifies the following limit for plastic design. LPD is expressed as the following 3.20. M1 and M2 are the smaller and larger values of the two ends moments unbraced segment. The ratio is positive for reversed bending and negative for single bending. The nominal capacity for different buckling cases in AISC design strength beams with compact sections are divided into several cases and calculated accordingly. As shown in Figure 3.7, the following equations are for the AA symmetric shapes and channels. Case number 1, plastic design. You can see each parameter should be satisfied as the following 3.21. Case number 2, no instability. In this case, instability of the beam is prevented and the full plastic capacity can be developed. However, the beam may not possess as significant deformability as case 1, so LB is expressed as formula 3.22. Note: section slenderness requirement may govern. Now next is case number 3. In elastic LTB, each parameter should be satisfied as the following 3.23, where CB is a modification factor for moment gradient. FR equals to 69 millipar for rolled shapes and 114 millipar for welded shapes. The corresponding parameters can be expressed as the formula 3.24 to 3.26. Last is case 4. Elastic FLT, each parameter can be expressed as the following 3.27. Now, here is the effect of moment gradient. Recognizing the positive effects of moment gradient, a modification factor CB is used for the above strength calculation. Referring Figure 3.8, CB is expressed as the following 3.28. Mmax is the absolute value of the maximum moment. Ma is absolute value of moment at LB to 4. Mb is the absolute value of moment at half LB. MC is the absolute value of moment at 3/4 LB. You can see from the Figure 3.8, it shows the definition of different moment values. When moment is uniform on simply supported beam, CB equals to 1. Now you can see Figure 3.9 shows modification factor CB in different moment profiles. That's all. Thank you for your attention. See you next time.